In this video, we'll look at the chi-square test, and there's two versions of it. One is called goodness of fit, the other is called the contingency table. We are dealing with proportions, so this is usually defects or defectives, or it could be any proportion for that matter. It is attribute data, and other assumptions here are that you've got two samples, or in the case of a contingency table, more than two tables. Or multiple proportions. So to access those, you can access them from this page, and we'll first go to the chi-square test. The chi-square test is actually very straightforward. The first thing we do is construct our hypothesis statement. So let's suppose we're going to flip a coin, and we'll flip that coin 100 times. We assume that there's really no difference in the number of heads versus the number of tails that we get out of this 100 toss result. So we say that there's no difference between the heads and tails kind of result. And in the alternate, there is a difference. We pick a confidence level. This case, it's 95% confidence. So what we expect to get is our 50 heads and 50 tails. And we lay that in here, and then we flip our coin and observe what the result is. So in this case, we get 63 heads and then 37 tails. And if that were the result, the conclusion is we would reject the null hypothesis. Now remember what the null says. The null says there's no difference between the results between heads and tails, and we're saying we need to reject that. So there's sufficient evidence here that within the results that they're not due to random chance, but in fact that the coin is biased somehow. So that is the chi-square goodness of fit test. The next one we're going to look at is the contingency table. Now this one's a little more complex, but it's still not difficult. Again, we construct our hypothesis statements. We're going to look at the defects or defectives by shift. Maybe we've got 3 shifts and we want to know whether or not the proportion of defectives is the same across all 3 shifts. And let's say these are the results over here. So the first thing we're going to do is construct our hypothesis statement. And the hypothesis statement says that the defects from shift 1 are equal to the defects from shift 2 and shift 3, and the alternate is that at least one of them is different. Our confidence level, 95%. Now the way this is constructed, we lay this, I want to take these out, and we'll actually walk through this. So I'm going to lay these numbers in here. This is the observed, so remember this is the results. We collected our data. These are our results. So in the first shift we had 43 defectives and 965, so we lay those in here. 43, 965, and then we've got 56 and 878, and then 68 and 781. So those are the results. Now what would we expect to get? And that's where the complexity comes in. The first thing we're going to notice is we've got 167 defectives out of 2,791, and we would expect to see that same ratio across all 3 shifts. So we're going to just go ahead and key that in. So it's 167, and we'll divide that by the 2791. But then we need to multiply it, of course, by the number of units that were observed or collected in shift 1, so 1,008. So we'll just go ahead and put that in there. So we've got 60 that we would have expected. And then similarly for the non-defectives, we've got 2,624, divided by 2791. So we key that in as well. So 2,624 divided by 2791, and then of course we multiply that by 1,008 as well. So on the first shift, given the ratios that were observed, we would have expected to see 60 defectives and 948 non-defectives. Now what we can do is simply take this and copy it over to the next 2 shifts, but there is one difference, and the difference of course is on the second shift we need to change, we're not going to use 1,008, we're going to use 934, so we'll just key in 934 here, and then similarly we'll do that for the non-defectives, so 934. And what we would have expected on the second shift are 56 defectives, 878 non-defectives. And then on the third shift we have to make a similar adjustment. In this case we're going to use 849. So we'll go up here and make it 849. And then finally, we'll make that same adjustment here at 849, 849. So this is what we observed. This is what we would have expected based on our observation. And then, like all of these tests, of course, we are calculating a test statistic. In this case, it's the chi-square 11.48. We've got a critical value based on 2 degrees of freedom and 95% confidence level of 5.99, and an equivalent p-value of 0.0032. Now you can see that the p is considerably lower than the alpha, and then when the p is low, the HO must go, so we reject the null hypothesis. And the null hypothesis that we've got equal defective rates on 3 shifts would not be a true statement based on the data that we've collected and the analysis that we've done. So at least one of the shifts, it would appear, has a defective rate higher than the other shifts. One challenge with this analysis is it doesn't tell us which one. To find out the answer to that, you'd have to use what's called ANOM, analysis of the means, but more specifically it's actually ANOP, or the analysis of the proportions, and that'll tell you specifically which shift has the higher defectives. And that is the chi-square test.